As a chemical property, how would you write it out? Okay. For which one, metathesis?
Yeah.
All right, so for metathesis, we're looking at HCl, so we have H plus and Cl minus. And then for H plus, this is acid, and so this is going to overlap with what we talked about acids and HNO3. So it's the same type of deal. And so what this means is this acid reacts with all bases stronger than what? Okay, well, it reacts with all bases stronger than this chart is a little bit tricky to use, especially with the strong acids here. So we got HCl here. It's in the middle of the strong acid range. And then you'd like to say that HCl will react with all bases stronger than chloride. But the problem with this region here, what is the problem with that region? The problem with that region there is due to what effect? Blank effect. What was that effect called? The leveling effect. So we have a problem here. The leveling effect means this, that all of these will react with water. And they'll react with water to produce hydronium or H+. H+ is just short for hydronium. In fact, H+ doesn't even really exist in nature. So when I write H+ like this, I really mean hydronium. But I don't want to write hydronium formula out all the time because it's just a pain. The reason why H+ doesn't really exist stably is because of this. What is H+ made out of? Well, H+, let's start off with H. H is made out of a proton and an electron. So if you have H+, you remove that electron and all you're left with is a proton. How big is a proton? Well, a proton is this nucleus, and the nucleus is tiny compared to the atom. And so they say, let's say if the hydrogen atom were like a football field, then the nucleus would be like a golf ball or something like that. And so it's about 10,000 times smaller. So when we go from a hydrogen atom like this to a proton or a hydrogen ion, that's about 10,000 times smaller. Now, Coulomb's law says that we are interested in the charge to size ratio. The charge to size ratio tells us the charge density. The more the charge is packed into a smaller volume, the higher the charge density and the more reactive that is. And so it turns out that H+ is just way too reactive. That's just a single proton. The single proton is tiny, and that has a full +1 charge. We can compare that to lithium ion. If we compare that to lithium ion would have 3 protons, some neutrons in there as well. Maybe I should do helium or something like that. But lithium has core of 2 electrons and then 1 valence electron. And so this would be lithium. If we look at lithium ion, we've lost that valence electron, so we'll have our 3 protons with some neutrons in there, and then our 2 core electrons, which would be in the first shell. And so this +1 is huge, tens and tens of thousands of times bigger than this, or maybe 10,000 times bigger, 10,000 plus times bigger. And so there's a huge difference in reactivity, whereas lithium is the smallest, well, of the group 1 metals. Hydrogen is small. Lithium is the smallest of the group 1 metals. It's still big, as the ion here. And so there's no comparison in reactivity of these. This is just much, much more reactive than this. This being so reactive, if there's water around, it attacks the water immediately, and therefore none of these acids here can exist in water. All of these acids will attack water to form hydronium. And hydronium is the strongest acid that can exist. So when we talk about reactivity, it's a bit tricky here because normally the way we use this chart is we say that, okay, if HCl got in a tug of war with Cl, and so they're both trying to pull the hydrogen. This chlorine's trying to keep the hydrogen, this chlorine's trying to pull it off. It's going to be a tie. So we need a base stronger than this. Well, a base stronger than this would be anything lower. But because of the leveling effect, all these are equal. In fact, all these bases are so weak, we don't even really consider them bases. We consider these neutral. All right, so the way I frame this is that it reacts with all bases stronger than or equal to water. Or equal to water. So even though nitrate is a better base than chloride, they're equally weak. And so nitrate's not going to do anything. Chlorate's not going to do anything. Bisulfate as a base is not going to do anything. Chloride, bromide, iodide, perchlorate, none of these are going to do anything. But if we go to trichloroacetate, yes, those will react, and anything below here will react. Speaking of, this kind of Coulombic thing, size and charge matter quite a lot. We can talk about this. Yeah, this is noble gas here. Noble gases are very unreactive. They have a full shell. But we have radon gas here. Radon gas is radioactive. And what that means is the atom itself is unstable. And what about the atom? It's not the electron, it's the nucleus of the atom is unstable. And so in radon gas, a chunk of the nucleus breaks off. And that chunk of the nucleus is called an alpha particle. So radon gas is radioactive, and we get alpha radiation, or alpha rays. Do you know what alpha rays are? Alpha rays are particle radiation. We have electromagnetic radiation and particle radiation. Alpha particles consist of helium atoms with a 2+ charge. And actually, it's 2,4 helium. So 2 protons, 2 neutrons, and a 2+ charge. So when we look at this, what does it consist of? Well, it consists of a nucleus with 2 protons, 2 neutrons, and no electrons. And so here, alpha particles are, it's kind of interesting. Radon's a gas, and radon's radioactive. Are alpha rays radioactive? That is alpha radiation radioactive? Radon's radioactive, but are these radioactive? And alpha rays consist of helium nuclei. And it turns out, no, they aren't radioactive. So if alpha particles and alpha rays aren't radioactive, then why are they so damaging? You know why they're so damaging? This is Coulomb's law. Coulomb's law, alpha rays are so damaging because you have high charge, +2, concentrated in a tiny, tiny volume. High charge concentrated in a tiny, tiny volume. High positive charge means electron poor. What does this want? This wants 2 electrons. If it gets 2 electrons, then it's back to being a noble gas. A noble gas with a filled shell, and it's going to be very unreactive. And so, what is the most powerful oxidizer on the redox chart? What's the most powerful oxidizer on the redox chart? Fluorine. Fluorine. Fluorine's the most electron-poor species on that redox chart. What about alpha particles? Are alpha particles more electron-poor than fluorine or less? What would your guess be? You know, fluorine just wants to fill its octet. Fluorine is just one electron shy of filling its octet here, right? Filling out its outermost shell. But what about helium? Helium, you know, helium 2 plus is 2 electrons short of filling it. The other thing is, when we look at fluorine, fluorine's got, 9 protons, 9 electrons. It's got a filled core, which is the helium core, and then the valence electrons surrounding that. This one doesn't have any electrons. This is just an exposed nucleus. And so what this means is this. Why alpha particles are so dangerous is because they're a more powerful oxidizer than fluorine. And so if we think about fluorine as being at the top, no, it's not. Alpha particles have that beat by a considerable amount. And so the way to think about this is, is you don't need oxygen to combust things. If you have fluorine gas, did I tell you about when I was in the Boy Scouts starting fires? In the Boy Scouts, we used to have to bring steel wool. And the steel wool would catch on fire, and then that would ignite the wood. And you always think, wow, steel wool is made out of just steel, iron. And why does that catch on fire? Well, iron is a pretty good reducing agent. The reducing agents give up electrons. Reducing agents are also known as fuels, so we can burn it. But if you brought a steel bar, it would be pretty hard to catch a steel bar on fire. So if I had just some steel like this, and tried to catch my tongs on fire, is it going to be easy to catch? No, it's going to be really hard to catch. But steel wool, has a lot of surface area, so it's a lot easier to catch on fire, even though it might be made of the same stuff. But that's burning it in oxygen. If I burn this in fluorine, no problem. If I use fluorine instead, it's a much more powerful oxidizer than oxygen, and I can burn steel in it without any trouble. So in terms of oxidizers, fluorine is actually, I used to work with fluorine when I was at UCLA. And when I worked with fluorine, I used stainless steel lines. The fluorine would eat up the inside, but it would form a barrier layer, what we call a passivation layer or inert layer. And so the stainless steel was okay, except for the valves. I had a gas line with a lot of valves, and the valves had a Teflon seat on the valve to close it. And the Teflon would be eaten up by the fluorine gas. And so I had to replace the valves maybe once a week or once every 2 weeks. I put new valves on there. Well, one time I went to reach up and to close one of the valves, and as I reached up, I wore 3 pairs of gloves when I worked with fluorine, heavy gloves. I reached up to close the valve, and then my gloves caught on fire. Then I knew there was a small fluorine leak in my line. It was coming from the valve, and so that's how powerful of an oxidizer it is. Fluorine is extremely powerful. So just imagine if you inhaled that stuff. If you inhaled fluorine, and the way we kept the fluorine is we kept it in a steel box. So if there were any leaks, it'd start eating the steel box first, so you can escape out of the lab. You just run away. But this is really nasty stuff like ozone. And so fluorine, imagine inhaling fluorine. Well, then imagine this. Imagine inhaling radon gas. Radon gas are lots of granitic soils that release radon gas into the air. You inhale the radon gas, the radon atoms decompose, the chunk of the nucleus breaks off. That chunk is called the alpha particle. And you've inhaled those alpha particles. Now the alpha particles are going to be seeking out electrons. And what has electrons? Well, your tissue, your lung tissue, your throat, all that soft tissue has electrons. And it's going to start attacking that to take those electrons to form helium gas. And so these are extremely powerful oxidizers. The situation, though, is we're normally exposed to a lot of oxidizers, like our skin. Our skin gets attacked by oxidative processes, but the cells in your skin have repair enzymes to fix any oxidative damage. But your lungs don't have that because your lungs aren't necessarily exposed to the external environment, and there are no repair enzymes to fix that damage. So this ends up causing cancer, lung cancer and that kind of stuff. Even though this is not radioactive, it's just a powerful oxidizer. It's going to cause DNA damage if that comes in and takes electrons from your DNA. All right. So let's see. Let's get back to what I was talking about. And so we have this. This is very reactive. So H plus just means H3O plus, essentially. Either one of those. Now, how do I write for chloride? And so when I think about chloride, for metathesis, I think about what cations is chloride like. And then I go back to the solubility rules. The solubility rules are chlorides, bromides, and iodides are all soluble except for. So in combination with any cation, they're all soluble except in combination with silver ions, lead 2 ions, and mercury 1 ions. All the other cations don't react. They won't precipitate. They'll just stay away from each other, go their own way. And so as far as metathesis properties go, chloride just reacts with 3 cations: silver, lead, and mercury. All the other cations, no. All right, and then we're done with metathesis. Okay, so what you want to do is you want to do the acid base, for HCl. Normally we think of HCl, hey, wait, HCl is only an acid, isn't it? It's not a base, is it? But what we do here is we do it like this. When we look at HCl, HCl consists of H plus and Cl minus. H plus, this is a strong acid. And this is an acid that reacts with all bases stronger than or equal to water. So we could write the same thing here for acid-base properties. And then chloride is a base. But we have to put a little asterisk here because we know about the leveling effect, and we know that the conjugate bases with strong acids are so weak that they don't react with anything. And so here, chloride is so weak that it's too weak to be basic in water. Therefore, it's neutral. But this chart here is what we call Bronsted acid-base chart. And so when we say it's neutral, it's only neutral for Bronsted. There's another type of acid-base reaction that we have to consider. What's the other type of acid-base reaction called? Arrhenius is too simple. We want to go to a more broad, more general. In other words, it's too specialized. Lewis. And so this is for Bronsted. We also need to look at Lewis, which I haven't talked about at all, but we're going to talk about it today. Keep that in mind. Okay, then we look at redox properties. And then we look at H plus and Cl minus. So here we have H plus. If H plus gets in a tug of war with H, So H versus H for electrons, which one's going to win? It's a tie. So what we need is we need H plus, and we need a reducing agent stronger than H2, which would be lead. And that would be the first one. But we don't know because this chart is not comprehensive. So, you know, we might say, okay, H plus will react with any reducing agent stronger than or equal to lead, but there might be a reducing agent that's stuck in here that we don't see because the chart is not comprehensive enough. And so what we're going to say here is this is an oxidizer, and it's a moderate oxidizer. It's not one of the most powerful oxidizers, but it's a moderate oxidizer that will oxidize reducing agents stronger than H2. And so what that means is that the H plus will react with lead, tin, iron, zinc, aluminum, magnesium, sodium, calcium, potassium, lithium, and whatever else is not on there. And so if I had, let's say, steel like this, which is iron, and put this in HCl, what's going to happen? The HCl is going to start to oxidize this, and it's going to eat up the iron. So that we no longer have iron metal, but we're going to have iron atoms in solution, so it's going to start to dissolve the steel. So don't keep HCl in an iron pot. If you keep HCl in an iron pot, it's going to eventually eat through it. Could you keep HCl in a copper pot? Yeah, there's no problem. You could keep HCl in a copper pot, and it wouldn't react. That's hydrochloric acid. Could you keep nitric acid in a copper pot? Let's take a look. So if I had nitric acid, would you keep it in a copper pot? No, it's going to eat right through it. If you had nitric acid, would you put it in a silver pot? Let's say you have a silver pot. No, because if you put nitric acid in a silver pot, it'll eat right through it. Could you put nitric acid in a gold pot? Well, where's gold? Well, gold is actually up here. Gold didn't make this list, I guess, because it's not as common, but it's up here. Could you keep nitric acid in a gold pot? Yes. Platinum's up here as well. Could you keep nitric acid in a platinum pot? Yes. In fact, I used to have, when I worked at the UCSB, I used to have a whole assortment of gold pots and platinum pots to cook chemicals. And, you know, you could have hot fuming nitric acid and not worry about the nitric acid eating through your container. You know, and so it works quite well. Those are expensive, though. There's cheaper ones like ceramic pots, aluminum oxide. You know, aluminum oxide is called alumina, and that's a very, very strong ceramic. What makes aluminum oxide so strong? I had a whole bunch of gold, platinum, and aluminum oxide pots. Actually, more than that. I had amorphous carbon pots. Amorphous carbon pots are like diamond in a way, because they're held together by those kind of covalent bonds, but much cheaper. But anyway, what makes aluminum oxide such a stable, strong material? Well, in other words, stable, strong material, that means it has a strong lattice. What makes a strong lattice, ionic lattice? Well, think back to Coulomb's charge and size. Aluminum ions are very small, and they have a high charge, 3+. Oxide is pretty small, and it has a charge 2-. And so when you look at Coulomb's law, we have Small ions with high charges makes a very strong lattice. This stuff is incredibly tough. Okay. All right, then we go and we look at chloride. Here. Chloride here. And then we figure out what chloride would react with. If chloride gets in a tug of war, what would it react with? And so take a look, and then I'll be right back, and I'll cover it. This one minute. Okay, so here, chloride reacts with what? Yeah, it'll react with all oxidizers stronger than chlorine. So what is that? It would be like lead-4 oxide. So if I take some lead-4 oxide and put it into hydrochloric acid, what's going to happen? What's going to happen is that lead-4 oxide is going to oxidize the chloride, and it's going to convert the chloride into chlorine gas. Fortunately, chlorine gas is not nearly as hazardous as fluorine gas. You know, fluorine gas is a lot smaller, much more reactive. Chlorine's bigger, less reactive, but still it's pretty toxic. And so we get green, yellow plumes of chlorine gas that can be generated. What's this? Permanganate. So if I mix permanganate with chloride, I'm going to generate chlorine gas. But when we look at permanganate, we're going to need some of this. This is acid. And so we need some permanganate with acid. Why do we need the acid? We need the acid there to form this. And that's a common theme for a lot of these. A lot of these we have plus H plus. Take a look, plus H plus, plus H plus, plus H plus. All of these that have the plus H plus, what do they have in common? They have water. And so water is pretty stable and a favorable product to form. So if we can form water, that's much better than just forming oxide. You know, if we didn't have the H pluses there, we'd be left with the oxide ion, which is a powerful base and not so stable. So permanganate and acid, hydrogen peroxide and acid, ozone and acid, or fluorine will all generate chlorine gas in this reaction. Okay, so those would be the chemical properties of this. So what we say here is that, chloride, this is a reducer, reacts with all oxidizers stronger than chlorine. Cl2. All right, are there any questions on this? So why don't you guys try this now? Why don't you guys try working on sodium nitrate, which I had, and sodium dichromate. tell me the chemical properties of those. You can work by yourself or you can work with others.